So I have been talking about peculiarities of quantum correlations, and in addition to understanding algorithms, there are other topics in which this subject has connections, and I will point out two of them. One of them is called quantum games. What this is a rephrasing of known ideas about quantum correlations in a different setting. In particular, what is done is measurements by two parties are mapped to actions of two players. It can be done without too much trouble. Various things are measured by two parties. In the correlation business, you can say that there are two players in the game and they are going to act according to certain rules. And knowing the peculiarities of quantum correlations, the consequence is that the player with quantum strategy has advantage. How much that advantage is and how you can evaluate it, that is the same logic as which goes in quantum correlations, but for that you need to specify the setting of the problem, who are the players, what are their options, how they make their moves, all those kind of things. It's an algorithm, but it's a very simple conversion from one language to another. And I have given one of these examples as an exercise in the assignment. Okay. And if you want to know more about it, there is actually a lecture or seminar of this Friday by Diptiman Sen in Center for Nanoscience at 3 o'clock. Okay. So this is one topic, and the other topic which is not too far away when you start talking about games is economics. It makes heavy use of making models which are based on certain type of games. It's a multi-party game, lots of players, they do various things, but the point is everybody wants to win. Okay. And so there are possibilities. It's but what are the rules? And the rules come from essentially constraints that the available resources, whatever may be, are finite. So there is going to be competition. And in competition, somebody wins, but then somebody also loses. Okay, you can't make a profit and nobody else will make loss. That generally doesn't happen. If everybody wants to make just a profit, then you just change the overall scale of the currency and everything remains more or less unchanged. That is inflation. But that is not the common scenario. Most of the time resources are finite. So they lead to competition. And how do you encode this kind of constraint in economical strategies? They are generically referred to as zero-sum games. Somebody wins, somebody loses. Okay. And here there is a lesson which economists kind of learned the hard way, and that is illustrated by what happened in the market crash of 2008. And that was that statistical modeling which generically is referred to by probability weights. Of the type e raised to minus beta h, which is the language of statistical physics. You have a distribution, you have various weights, and you can calculate averages and various properties of distribution based on that. And this is not enough. And at the time of that market crash in 2008, the algorithms were various dealers were using were all based on this kind of statistical modeling, calculated various probabilities, gave them certain weight, and see what happens. The part which got left out is the business of zero-sum constraint. And how do you include that here? The very important property buried inside it, the statistical weights are all positive. If you want to include competition, you have to put some weights negative. Somebody wins, but somebody loses. And the market crash happened because this part was missing. And so after learning this lesson about the economy going crazy, the people had to revise their model to include negative weights in this distribution and calculating various averages. And that is now the current refinement. They had to hire lots of physicists who had some background of how to deal with negative weights. The mathematicians were too much buried into probability theory, and then everything went okay, and the models basically improved. They could understand what happened in the market crash. So that is another related area, but the principles are something which we can understand. And that brings me back to whatever I was describing in the last lecture. Wigner functions. They are essentially weights in the phase space which sometimes can go negative. And the peculiarities of whatever happens is because of this extra possibility of having negative values. So this WXP real, but can become and people who know quantum theory that could help these economists about how to deal with such situations. So let me write down the continuum definitions which I used last time. Which is, it's a Fourier transform of the density matrix in the relative coordinate. And it has the usual normalization constraint that total weights add up to 1. But somewhere it can be negative, somewhere it can be positive. You add everything, then it is okay. So this is a continuum language, and now I want to translate into the discrete space, which we are much more comfortable in dealing with while talking about algorithm. So how do you discretize it? Well, you have to do two things: make the variables discrete, and also then go to a finite number of states. So I will do it in 2 steps. So here both of them are real variables. They are all minus infinity to infinity. I can go from real variable to integers. And this is something which is well known in studying solid state physics and crystals. You take the position, there is a momentum, and the conjugation relation between the two variables hold. And what happens to the situation where instead of having x continuous, x is just a set of lattice points. Okay. That converts the range of the momentum, and that is bounded, and the typical notation which is used is there is a range of variables which is called the Brillouin zone, going from minus pi to pi, and the momentum which rescaled, so this p is equal to h cross times k. You factor out this Planck's constant because all these things become easier to write, and this is bounded. This one is the whole set of integers. But this is real. It's still real, but it's a finite range. And what does the corresponding label for the density matrix that I can write down? So I can label this thing as W of, well, I could write is n for integers and k for momentum, and there is a little rescaling I need to do. So h cross goes away because I replaced this p by k, so that is fine, but there is also a rescaling which does with this 2 pi gets reduced to pi, and the integrals are now restricted. Let me get the normalization convention the same as whatever I typed in, and it is a dummy variable which I have to sum over. Okay. So I won't write the integral. The y is just the same coordinate as x, so it is an integer row of 2 indices, and e raised to 2 I k times m. Yeah, that's it. So what all happened in this? First of all, I rescaled this variable from p to k. So this h cross disappeared over here, and I rescaled the corresponding variable here, so this h cross disappeared. On top of that, I had a integral here over y, but the variable here was half y. Now I certainly cannot make half an integer as part of the summation, so I doubled the allowed values of y, which is the responsible for replacing y over 2 by m, and then this factor changed by 2 for the same scaling, and in the summation another 2 got eaten up by this rescaling of y. So it's just a straightforward definition, but now I have a description in this works, properly normalized, and you can calculate whatever expectation values you want, and I gave the rule for the expectation value also last time, that O was equal to, well, I will write it in the continuum language, you can translate it. The only thing you have to make sure is that this operator has a suitable form. It has to be something which maps to a Hermitian operator in quantum theory. Once that is done, the rest of it is a trivial normalization, and you can fix it by saying that if the operator is identity, this integral should be 1 in consistency with this convention. So you can fix the operator for whatever you want to calculate without too much trouble. Okay. So this is quite okay, and now I want to go to finite dimensions. Where the set of integers which are here are not infinite, but some set of values, I can call it, say, d dimension. Then I can naively convert this to a form, which I will now call W. I have to invent two labels. Again, let me make it consistent with my notes. Okay, I can still call it Wn and K, that is fine. And the normalization will be 1 over the D. There will be dummy sum which goes from certain values of M, and afterwards I have rho of n minus m and plus m and a phase which now has to again be relabeled, and I rescale in terms of these dimensionality to make things consistent. So the D actually plays a role similar to this Planck's constant in this notation, and there was a H cross which gave 2 pi I, and in this discretization that got doubled, and so I have now here 4 pi I sitting over here. So this works, but only when D is odd. And with integers in the modulo D arithmetic. Why modulo D? Because this is finite, some set of values. Here I can keep on multiplying everything by D, and I have to basically bring the phase back to itself. But the reason for this peculiarity is that I have to add only integers over here. So I start with what happens is M, it is n, which is well defined. Then it will become n minus 2, n plus 2, n minus 1, n plus 1. The difference between the two coordinates is 2, because these things are restricted. Then the next difference will be 4. What happens to the contribution where the difference is odd? That thing is completely missing. And so, the way this still works, that if I do a modulo D arithmetic, D is odd, I'm changing the differences by 2. The first cycle it will cover all the even numbers. The next cycle it will cover all the odd numbers. So I get these definitions correctly, where if I keep on looking at the argument, the arithmetic will repeat after going through 2 cycles of ZD. It is also buried inside particular here that there is a 4 pi I over here. So one range of 0 to D minus 1 is not enough. I need to go from 0 to twice D minus 1, and then afterward the phase will start repeating. Okay. So this is something which is little strange, but that is what happens when you try to make this thing finite. And if you plug in this formula and make D even, you will immediately see that half the points are left out. It doesn't cover the complete structure of the density matrix. So you have to find an alternative. And
sir, even if it is 2D minus 1, the difference is still even. Even if the weight is increased to 2D minus 1,
yeah.
the difference is still even, right? Minus 7%.
Yeah, but it is calculated modulo D. So even number modulo an odd number will produce an odd number in the second cycle. You need to cover 2 cycles because this will go outside the value of D, and then you have to do modulo D calculation. And the constraint is basically coming from the fact that there was some y over 2 over here, and I'm trying to make it an integer, and there is trouble when this number is converted to half integer. That's not there in my set, so I have to find some other solution. And alternative is needed for even values of D. The simplest example is 1 qubit. The even value of D, to try plugging this thing, it doesn't work. And 1 qubit is something which we have used all the time, all over the place, so we have to find a solution. What helps is, if I want to look at arbitrary integers, well, there is one structure which remains unchanged in this whole construction, that you still have a density matrix. All you are doing is combining with particular weights. And density matrix lives in a Hilbert space which has a tensor product structure. Okay. So that tensor product structure for the density matrix doesn't get disturbed by doing all this jugglery. So all you are doing is some linear combinations. What have been factored into tensor components, it will remain. They will all get rescaled by some numbers, that is fine. So the density matrix has tensor product structure, in the Hilbert space, which carries over to W, whatever it is. And so if I'm given some arbitrary D, I can factorize it into components, and then we can easily see that any integer is some odd number multiplied by power of 2. And so I can construct the density matrix and hence the Wigner function for arbitrary D. If I know how to do it for an odd number and how to do it for 2, I will just take the tensor product afterwards. And that is a rigorous mathematical procedure. I don't have to invent some new formalism. This is a valid procedure to construct. So the question then comes back that I have to find some solution for d equal to 2, which is 1 qubit. Then the whole problem is solved. So what do I do? We know the general description of a density matrix in the standard notation, which is analog of, say, the position space coordinate, which is given by the Pauli matrix is an identity matrix. It is geometrically the block sphere. Okay. And if R has magnitude 1, you are on the surface of the sphere. Magnitude is less than 1, you are in the inside. So this is the density matrix, which now I want to convert to this Wigner function description. And I have to go back to the initial definition. What do I want to do? I am doing a Fourier transform here in the relative coordinate. Do I know Fourier transform, how to do it in this two-dimensional space? And the answer is yes, we have gone through that. And the Fourier transform is implemented in this space by the Hadamard matrix, which is explicitly 1, 1, 1, minus 1. And if you want to write down how it connects the coordinates, so there is this identity can write it either way. That is what the Fourier transform in two-dimensional space does. It takes, well, let me write 1 and 3 instead of x and z. We keep lighter, more abstract, 3 Pauli matrices. But it converts sigma 1 to sigma 3 and vice versa. Okay. Whatever the variables over here, x and p, the conjugate pair. So it tells me that I should treat variables 1 and 3 as the conjugate pair. Okay. So sigma 1 and sigma 3 form conjugate pair. What does it mean now in terms of the original description? This was a state in the phase space, and the classical language was that the particle which you are looking at had some position and some momentum. Okay. Quantum mechanics doesn't allow it. It says both of them cannot be specified arbitrarily, precisely, simultaneously. They will smear them out. And that was the consequence of having this Planck's constant stuck in over there. So here now I have to develop a language where I will say that the state is specified by some value of the sigma 1 component and some other value of the sigma 3 component. I know that because of the uncertainty relation, they will not be precisely defined, but I will then write them as distributions. over there where some things can go negative. It is fine. I have to accept that in case of Wigner functions. What is the constraint that this so-called marginals which here were obtained by either some over all the momenta or all the positions that gave me the actual probability, mod psi x square, etc. So when I do a specification of sigma 1 having some value, sigma 3 over some other value, both are they are the two coordinates, but if I sum over one of them, then I should get the operator which says either sigma 1 or sigma 3. And I know what those operators are. What are the operators which give the corresponding values when only one of them is involved. So marginals produce projections. These are the analog of probability density. So and given by the corresponding weights, which is the projection operator is half of identity plus sigma 1 if I am measuring that. Identity plus sigma 3 minus sigma 3 depending on the eigenvalue being plus 1 or minus 1. These are the projection operators which should come out from the marginals. And that is actually enough to cook up a model. Okay, it basically looks like a trial and error business, but there is no other choice. Okay, so what can be done is now I will just to give a assignment for various operators. So these restrictions it produces a map, and there are 4 components over here. I can write it in any basis I want, but it is generally convenient to write what is the map for the identity and the 3 Pauli matrices. So the identity maps to, well, nothing very complicated. Everything has the same weight. And where does the half come from? It comes from this normalization constraint that if I sum over all the components, I should get 1 or the whatever trace of rho is equal to 1, which produces this normalization half, because trace rho involved half the identity, and identity is half this matrix. If I sum over 4 possibilities, there is 4, 1 half coming from here, 1 half coming from here, and then it balances it out. This one don't contribute to the trace at all. Okay, so this is a normalization. Now I want to construct something which describes sigma 1. It has to be a 2 by 2 matrix. It is the density matrix, just a different representation. And with the condition that if I sum over these marginals. What do they mean? They means either you take a sum over all the elements in the row or all the elements in the column. Those are the two marginals where you say I integrate over all the x or all the p. So the x and p are now rows and columns inside here in this matrix notation. And the answer is the convention of half still continues. Something like this, where if I have to say what I map to map. So one is an index which I map to the column number. So if I sum over the other index, which is 3, which will be mapped to the row number, what I will get is a +1 and -1, which is what exactly I need to construct the projection over the +1 eigenvalue of sigma 1 and -1 eigenvalue of sigma 1. Those are the two probabilities. And the corresponding choice for this is now the whole thing flipped around. So now I get the projection operator if I sum over all the elements in the row. But remember what the marginals do, it says that if I sum over here all the column indices and sum over all the row indices, I should get the probability of that particular eigenvalue. And sigma 1 has some probability for being +1, some probability being -1, and those things are explicitly put inside here. Okay. The actual continuum coefficient is sitting over here. Eigenvalues of sigma 1 and sigma 3 are fixed. They are only +1 and -1. No other observable. What about the third component? What happens here? Well, I can't just multiply these three and get the number, because that is not the part which I have included in the formulation. I included the addition part, which is the superposition coefficient. I included the tensor product structure, but what happens when you multiply the polymatrices, that is something which is not the ingredient of this formalism. You just can't do that. But you can guess what choice will be available. There is a constraint which says that this, whatever this thing is, it doesn't contribute to the trace. So if I take trace, which is sum all the 4 numbers, it gives me 0. That is buried inside this +1 and -1 eigenvalue. There is nothing else. So can I write anything similar, which will have numbers adding up to 0? And the answer is yes. And this is the third choice. There is, of course, a half. But there is an ambiguity that I can put -1 on this diagonal, or I can put it on that diagonal.
If you take minus, the trace of root 2 will be 0. Why is it not minus? Because sigma 1 and sigma 3 is separate.
The eigenvalues will still be +1 and -1. That I cannot change.
No, sir. Normally, sigma 1 and sigma 3 is separately, the trace is 0.
Yeah.
So if you consider minus, then sigma 2 separate trace is also 0.
Yeah. Those are the properties, because polymatrices are in some sense all in a equivalent footing. I cannot change some basic properties. So the trace of any polymetrics has to be 0. The point is that if I just demand that and ask that something to be different than that, I get 2 answers which differ by a sign. Whether I put -1 on this diagonal or -1 on that diagonal. And there is a reason for this ambiguity, and that is connected with the structure of the SU2 algebra, or the group which describes the polymetrices. That SU2 algebra involved complex numbers. And here we made everything real. So something got eliminated, which is essentially the operation of complex conjugation. It has no place. But this ambiguity is related to that particular fact that I have an extra symmetry, which is complex conjugation. Which convention I choose? The original formulation says that it's a symmetry of the whole structure, so both the values should be allowed. They don't describe anything different. Both of them describe the same physics. But here, if they describe different physics, I have to impose both the constraints at the same time. Mathematically, I can write down this symmetry that sigma I there is fundamental identity obeyed by polymetrices, that commutator of 2 of them will give the third one. But this does not fix the polymetrics convention uniquely. And under this transformation, this is invariant. Okay. You are changing sign, so there will be an overall change of sign, but you are taking complex conjugate as well, which will flip another sign of this imaginary unity is there. And those things basically balance out. What is epsilon ijk ensuring that there are 3 here, 2 of them will be real, 1 and 3, and 1 of them will be imaginary. So when you do complex conjugation, these factors coming from sigma will flip one sign, because sigma 2 will be there somewhere and it will change sign. And this I will also change sign under complex conjugation. So this identity is unchanged under this particular transformation. And this uncertainty now gets reflected in this ambiguity over here. I did a mapping where everything got converted to real. So this complex conjugation has no meaning. But this is a flip of sign. It has to show up somewhere. And there are 2 choices which are left. And conveniently, we'll put them in sigma 2, which in the standard basis is imaginary. Let the other 2 remain simple enough. We could have put it in either of the 3 matrices, but it's convenient to put it over there. So this complex conjugation symmetry leads to and both when you do a actual calculation, you have to ensure that both choices should work. Otherwise, you lost out on something which is fundamental in the SU2 algebra, and that comes out quite straightforwardly in any applications. So this is an assignment, okay, and I can now use this assignment to write general expressions. So I had this expression R dot sigma which describes the density matrix. What does it look like? And I have to add up all the pieces together. So it is first one is just 1, 1, 1, and 1. Then it's x, so Rx. Okay, let me just write it. What is minus 1 on the right hand side? Okay. Then Z was positive on the top and negative on the lower part. And why there is ambiguity, I will write it as plus or minus here and plus or minus here and the opposite sign here. So that will give me a description of any state. And now I can ask, what is peculiar in this construction, that are there places where this Wigner function, which are basically a matrix entries over here, they can become negative? And the answer is yes. I have known all the ranges given by the block sphere. So I just figure out which region this thing is positive, which region this is negative, all of them. Okay. So that is not too complicated because this is a linear combination of the coordinates. In a three-dimensional space, any equation like this will define a plane. And the coefficients over here will define the normal to the plane or something like that. So I have a block sphere, which is a sphere, and now there will be various planes going across it. So these values can be decided, so the regions where some element can be found by slicing block sphere with so I'm going to do that, give the picture. So I have to draw a three-dimensional coordinate system. Well, as well as I can construct my drawing. Let me draw the sphere first. Then there is the origin. Then I will draw some x, y, and z. Okay. What is this equation? And I want to decide whether the number is positive or negative. So I want to equate this to 0. That will give me the plane. One side will be positive, the other side will be negative. So it's easy to figure out where all these equations are going to work. And the first thing to notice is if I take some coordinate which is just the intersection of the plane with one of the coordinate axes, it will hit 0 somewhere or the other. The reason being that the vertices of intersection of the coordinate and the block sphere, they have one coordinate equal to 1, other two are 0. And I can find the entry over here where 1 and 1 will cancel out, the other two are 0. So these endpoints are going to belong to some planes or the other. And then you imagine a little bit of a geometry and you will find that the actual planes are nothing but triangles, equilateral triangle connecting these unit distances on the coordinate axis. And well, you have to extend it on the negative side as well, wherever there may be. And now with a little bit of imagination, you can figure out what this is going to produce. There are 6 of these vertices, +1 and -1, and you are drawing all these triangles of various types. And they form some structures which are, well, I draw it in some way, not too accurate, but there is one triangle over here, and the similar stuff goes over there. So there are 1, 2, 3, and 4 on the top sphere, and some 4 in the bottom hemisphere as well, etc. So there are 6 coordinate axis endpoints, and 8 triangles which triangular faces. Okay. And they form a regular octahedron. So we got this description, and it tells us that if I take any point in this three-dimensional space, if I am inside the octahedron, all the elements will be positive. But if I go outside and there are points which are in between the octahedron and the sphere, those places will have negative entries somewhere or the other in this density matrix. And those are the possibilities which are different, or in some sense they get mapped to these negative weights of the distribution. Yeah. R plus? This. There is no I here. Yeah, okay. I added that together. And half is, half I have not put. So if you put this half also, then that will become a quarter, but it's overall normalization. So the region between octahedron and block sphere and the sphere spherical surface gives negative weights. And these are the states which will play a role in many algorithms which are hidden in this construction for the time being. Okay. You can actually ask maximum departure between the triangle of a octahedron and the spherical surface will correspond to the direction which goes in the center of the triangle. Okay. So maximum departure, you can, that also is fixed along there are 8 directions, there are 8 triangles sitting here, and they can be easily labeled whatever they are. All 3 coordinates equal up to a sign. There are 8 combinations you can construct by plus or minus, whatever it is, and they will correspond to a direction which goes through the center of the triangle. It gives maximum difference between the octahedral surface and the spherical surface. So this is a geometrical description, and now there are theorems which tell you something unique about what happens when the Wigner function is positive and what happens when it can go negative. And I will just quote them. Proof is a little technical, but it's a powerful result. Well, I can give one other result also. Useful to see that I could construct this for a single qubit, but the state which is very important in analyzing all the correlation are actually Bell states. And you can ask what happens if I now construct a Bell state. And I will just write down the answer. So for the singlet, okay, all I have to do is tensor product. It's some combination of sigma on the first matrix and sigma on the second matrix. I do a tensor product of the two matrices with whatever combinations of sigma that can appear. So you may not have done it before, but it is a simple exercise to take the singlet state like 0, 1, minus 1, 0, construct the density matrix, which is a outer product of the two, write it as a linear combination of polymatrices. It can be done. And then you take the first polymatrix, convert it by this, second polymatrix, the same convention, construct a tensor product. What happens automatically that the sign gets squared. It doesn't appear anywhere, etc. And then you get a Wigner function, which is tensor product of 2 by 2 matrices with another 2 by 2 matrix. So totally it will be a 4 by 4 matrix. And I should get the normalization correct, which is trace of the matrix should be not trace. Sum of all the elements should be equal to 1. And the answer is this. Sixteen entries are there, all of them have magnitude 1, but the ones on the corners get -1.
This is for sign minus. This matrix representation is for sign minus.
Yeah, singlet state. This is if you take the other Bell states, you get again 4 entries which are negative, but these -1s are in different locations. And the normalization is fixed by the usual convention. You add up all the elements, 12 of them are +1, 4 of them are -1, and the sum has to be equal to 1, so the factor of 8 takes care of it. And now I can do this business. I can calculate any expectation value. How to construct the operator, but in case of Bell states operators are also quite simple enough, and what we calculated and compared with this experimental demonstrations was a correlation function which was sigma dot n1 which is what the Bell's inequality test involved. You measure first spin along n1 direction, another spin along n2 direction, you construct correlations, and if I now do this, I have the state already here. N1 and N2 I have to plug in by the same convention. You can figure it out. It's basically the same matrices but with different scalings. What will there will be 3 components, and they will be either included like this or that, whatever it is. And this result will produce the quantum prediction, which was that expectation value was minus n1 dot n2. This was a non-trivial check that classical answers produce something else, the quantum result produce something else, and it went outside the bounds. This description is enough to recover all the peculiarity of what goes outside the bound, and the reason being some of the entries are negative. If I had stuck to the situation where all the entries were positive, I would have gotten the classical bound. It cannot reach these values at all. But with the quantum input, negative signs take care of everything. So this is some exercise if you want to work out in detail. I'm just pointing out the result. But my more interest is in quoting the general description which concerns quantum algorithms, and that is this particular theorem. By these two people. What does it say? That I can associate always Wigner functions can be associated with initial state revolution operator and measurements. This is nothing specific to Wigner function. In any quantum algorithm, you do this. You have some initial state, you have some evolution operator, and you perform some measurement at the end. The point is that I can convert all the 3 in the Wigner function notation. Why? Well, the initial state is generally very simple, like all zeros. I can map it into this, not too much trouble. The evolution operators will be transformations using polymatrices or individual qubits. Well, I have constructed a mapping for that, so I can define that as a evolution. And the measurement will be a projection, and that will be calculation of some expectation value in the state. I can do that as well. So I have a description for all the three components, and this is what will happen in any generic algorithm. And the theorem now says that so the quantum evolution then can be interpreted as a phase space trajectory, and well, because it is quantum, it's not just one trajectory but a superposition of trajectory. So phase space trajectory superposition. I can calculate it all component by component and then add it up. Okay, just like here I did it with 3 Pauli matrices and then added it up. So that is fine. Again, it's a generic statement, but which that becomes is a sum of Wigner function factors for n qubits and t time steps. This is what we do in a computer. Some number of qubits are given, some sequence of time steps are performed, and now you convert everything in this discrete notation with Wigner function language. So that is also fine. And now comes the statement of the theorem. When all the terms in the sum are positive, this is a stochastic evolution process. People working with the classical algorithm will label this as some kind of Markov chain. We go from one step to another with some probability. And the crux of the matter is the sampling of this Markov chain requires an effort which is polynomial in NNT. Number of qubits and number of time steps. And these are all the algorithms which we consider easy, polynomial. And this is a strong statement that if you are given that Wigner functions, all the factors wherever they are all positive. I can make it as a stochastic Markov chain, and then everything is simple enough, which means that if I want something non-trivial, the Wigner function somewhere must give a negative entry. Otherwise, there is no option. So, non-trivial algorithm, there's a consequence. Need negative Wigner function somewhere. And what that somewhere will be is mostly in the evolution. Because initial state is all zero, whatever it is, you write it as a very simple starting point and don't play around with that. Measurements will be associated with some operators that you are not going to change very much. It is some observable you want to measure. All you can do is arrange this evolution operator, that is your software of the algorithm, such that somewhere a Wigner function which is produced becomes negative. But that is a necessary condition if you want to produce algorithm with some quantum advantage. So this is a powerful result, and it tells you a lot of things. And there is again a geometrical consideration which kind of follows that what are you going to do if you want to keep a Wigner function always positive, that if you are inside the octahedron, you want to remain inside the octahedron. What is the algorithm going to do? It is going to rotate all the coordinates. And so this vertex is here. In the next step, it might be pointing that way because the polymetrics got rotated. And so what is positive in one case may not remain positive in another case after you perform a transformation. But there are certain transformations which will leave this octahedron invariant. These are the symmetry groups of various geometries. And if your operations are the symmetry transformation of the octahedron, then the shape will not change, and then the algorithm will be efficiently simulated. Yeah.
Is there some correlation with the negative rates of Wigner mapping and the entanglement?
Well, it showed up here. Just have to do the work. This is an entangled state, and you produce these negative values.
So negative Wigner function means we have some negative entries in the matrix.
Some in the matrix, yeah.
If all the entries are positive, it's called positive.
It's positive, yeah. So entanglement will show up like this, some entries becoming negative.
So then if we consider that block field, on the surface of the block field by that construction, that is a negative Wigner matrix for the state rho.
Yeah.
But rho for on the surface.
So entanglement is a what you call a higher level process. It's one qubit. I cannot talk about entanglement. Entanglement requires two systems in a correlation. So that comes at the next stage. This is more fundamental than that. So the operations that transform the octahedron to itself can be simulated or sampled, let's call it simulated efficiently and the mathematical nomenclature for that is Clifford group. And how I can specify the Clifford group? Well, what are the operations which will bring this coordinates back to itself? I can specify in many ways. I can draw the real octahedron and imagine the transformation. You can classify as a, say, a rotation along this axis by some 90 degrees. That is okay. You can have reflection operation which will keep, etc. So they will make up this Clifford group, but there is an alternative way to define it, and which I had mentioned a long time earlier while discussing a reversible computation, that all you need to guarantee is this 6 vertices, they remain the same, and the octahedron will remain the same. I just have to point out the positions of the objects at the corners, and they do not change. And so there is a definition of a Clifford group based on that. That is the set of, yeah, you have to include the definition, this I, sigma 1, sigma 2, sigma 3, and we have to include when you multiply them there is an overall sign convention, so it could be plus or minus 1 or plus or minus I. All these things appear. So this is well, it's a overall factor, so it's a number, but the objects of transformation are these 4. And I can define the Clifford group as all operations which transform this set of objects to itself. Only permutation of various types. So they transform and this result was actually proved earlier before this thing, and this go by another name, which is labeled after again two person, Gottesman and Neil. And what they proved that any set of operation which transform this structure to itself can be efficiently simulated on a classical reversible computer. Okay. So that is a different way of putting this thing. This is more general in the sense that it included arbitrary Markov chains and description of various trajectories. This was a little bit simpler thing, just a algebra of polymatrices. If somehow the set of operators transforms within themselves, you cannot generate anything complicated in the algorithm. And that gives now a list. I will construct all the logic gates which transform within itself. What are the logic gates? Well, here it will correspond to rotation or reflection of this octahedron to itself, and anything which is in that logic gate is not going to give you a quantum advantage. Life is indeed simple enough for that, because in discussing the quantum logic gates, we did a successive simplification where everything was brought down to 1-qubit operations and 2-qubit operations. On top of that, the 2-qubit operation, we could always make it control knot. But control knot was already part of the reversible classical logic. So the new part is just the 1-qubit operations, which are nothing but some transformation of this. What are the 1-qubit operations you need to get quantum advantage? Just boils down to that simple particular fact, and I will give the description. We'll do the transformation of this octahedron to itself. What are the gates which will do that? And all those gates are not going to give you quantum advantage. So that is for the next lecture. The
octahedron is unchanged.
Yeah.
Quantum advantage is realized.
No, it's not. Because if it is left unchanged, what is inside remains inside. And all the interior points have positive Wigner functions. So if you start inside like a simple state with all zeros or something like that, you're not going to get out. And if you don't get out, you don't get advantage.
Is the Clifford group clear? No. Since the transform octahedron itself can be simulated efficiently.
Yeah.
Clifford group, if you have only 1-qubit state and gates acting on only 1-qubit, can't take Clifford group like.
Clifford group is for 1-qubit is just a symmetric group of the octahedron.
But we can't get quantum advantage by 1-qubit.
No, but it has to be in the algorithm. As I said, you can't write an algorithm with only 1-qubit gates. You needed a 2-qubit gate. 2-qubit gate was conveniently chosen to be control knot, and that is already there in the classical logic. So what is the quantum part left in that general algorithm are 1-qubit rotations. You need the 2-qubit part, which is classical, that is true, to get some interaction and some complicated evolution. But because it is classical, that part can be simulated efficiently.
So is there a generalization of Clifford group for that?
Yeah, so Clifford, arbitrary space, you can raise it to some tensor power n, no problem. Yeah, one more thing. Next week is the last week of the course. So, any questions you may have about the whole subject, or maybe not what I have talked, something else you want to get clarified, you bring your questions to me. It will be, in some sense, a tutorial where I will answer every doubt that you may have. Okay.